And coming to this mocha also, where recently 2023, like if you are seeing at Puri, we are compared with both WRB Gopalpur and the actually Wave Atlas data. We are like there is some deviation actually. We could get like 6 meter wave height was measured. This due to difference between, because the cyclone track is not passed near to the exactly to the station. It is away from the station. This is what, and like it will be like a little good agreement with the model and the data comparison matches. Due to this deviation, only deviation from the larger path, that if Machilipatnam also there shows more deviation. This conclusion is like these systems are very useful, which are installed near the Gopalpur and Puri. These robust systems like measures currents for every 1 hour and waves are for every 30 minutes or will be processed. These systems can withstand the high wind also. Like this antenna will be, we can withstand for high wind like up to 150 kilometers to 200 kilometer per hour. So that if you are taking the buoy data, sometimes may be drifted due to high wind or something point data, whereas this system will measure until the cyclone what is a cyclone passes through the cyclone track, and if buoy drifted it will be difficult to whereas HF radar measures from the land. This is the main advantage of the HF radar. And apart from that, we can understand the like coastal currents, majorly coastal currents and the eddies. East India coastal current we can understand from using this HF radar station. That is why every state we need actually two pairs, because to get the direction compulsory from one station we cannot get the direction exactly. We need at least two stations spacing at 100 kilometers based on the frequency to get the direction of the current. Thank you. Height of the antenna will, transmitter will be 7 meters, receiver will be 4 meters. No, actually like not like that. So that we will place it in the high elevated position where actually. Thank you. Because actually it will be taking salinity as a medium, it will travel. So no need if you are putting higher. It should not have the obstruction while the electromagnetic wave going to the ocean. Thank you.
Hello? So one of the shortcomings I thought is that you said you fit a particular spectrum. Uh, Now, one of the things that's of interest for the coastal modeling is actually the variation in the spectrum itself. Because if you take one of the standard spectrum like the Pearson-Moscow spectrum or some other spectrum with a variation of the forward part and the backward part of the mean around the peak frequency, then that's not how the spectrum vary in the shallow area, particularly near the coastal area. They have a lot of variations, and especially during the type of this cyclone. So I was just wondering if you had made any specific comparisons. Yeah, so that I think is a shortcoming. Yeah, okay, all right. But you can also get the wind. So you can get the current, you can get the waves, you can also get the wind. You can get the wind speed also. Okay, we can talk about it because that's the Bragg scattering, the intensity. they use from the satellite to measure the wind speed. All right, so we'll go over to the next presentation. The next presentation is very energetic. It's by two very young authors. They are third-year students, Muhammad Jalil and Sohita. So they would be talking about a study on the factors influencing hydrodynamic analysis on a shallow water region pipeline. Right? Sorry? Pipeline? This is not part of your title? Okay. Hydrodynamics in shallow and restricted waters. Sorry, the pipeline is the next topic.
Good evening, everyone. Myself, I am G. Sohita. Together with my colleague Muhammad Jalil, we are the students of.
Shallow waters.
Good evening. Myself, I am G. Sohita. Together with my colleague Muhammad Jalil, we are the students of Sri Narayana Gurukulam College of Engineering. We are currently pursuing BTech third year in Naval Architecture and Shipbuilding. So today we are going to give a literature review over hydrodynamics in restricted and shallow waters. So as the outline of our presentation, we are going to introduce about the main objective of our study and then the hydrodynamic forces, how they are influencing the performance of the vessel. And we have generated some analysis over the wave pattern and the resistance using some software. And the maneuverability part, how the underkeel clearance and the restriction of the depth is influencing the performance of the vessel. We are going to discuss over that. And as the conclusion, we'll be concluding the topic. So for the introduction, we all know that the shallow water, which is having very little depth, and also it is influencing the performance by inducing more hydrodynamic forces such as lift and the drag force, and these impact the performance of the vessel. And due to the form of this due to the form of the vessel, it will also influence the various pressure distribution which is there towards the bow and the stern portion of the ship. And because of this variation in the pressure distribution, there will be additional resistance components that will be acting over the vessel, whereas the frictional resistance, which is due to the viscous forces, and also wave making resistance and all, also show the impact over the hydrodynamics, which will influence the vessel performance. And the influence of drift angle will also be a factor which will depend upon the impact of the hydrodynamics that are acting upon the vessel. Hydrodynamic forces. Pressure distribution. As I already told that the pressure distribution is varying over the bow and the stern portion, which will amplify more resistance to the vessel. And due to this restricted depth of the water, we can also find the grounding of the vessel, such as the trimming, and the sinkage will increase for the inland water vessels. And the factors influencing the lift and the drag forces are the operating speed in which we are operating the vessel, the draft and the water depth, and also the flow velocity and the turbulence is also a factor in which the lift and the drag forces are getting influenced. And the wave-induced loads such as added mass, damping and the restoring terms can also influence the vessel performance, and consequences such as hull structural integrity can be an impact over that. We have generated a model by taking the lines plan from the following shipyard, Sea Blue shipyard of Kerala. So here, this is the length of the vessel is around 51.4 meters, and the beam is around 9.6 meters, and the draft is of 1.4 meters, in which that is a body plan, and this is a model generated using the Maxf software for our analysis purpose. There are three characteristic regimes in which we have generated about the wave pattern, in which the first one is a subcritical regime that the resistance encountered by the vessel is relatively low compared to the other regimes. The critical regime in which the brake power will be increasing dramatically highly due to the increase in the resistance, and also it is having less decreased propulsive efficiency. And the supercritical regime in which the brake power is smaller compared to the other two regimes. And this is the wave pattern generated. The first one is for the wave pattern at the fluid number of 0.18, and the other two wave patterns is for the 0.36 and 0.46. And this shows that the wave pattern changes will be associated from one regime to the another regime depending upon the speed. And also the high speed vessels will be generating large wake which may cause the bank erosion. Now I request my colleague to continue the presentation.
Coming to the resistance part, as we all know, in general, the fuel consumed by the vessel and the engine emissions are directly proportional to the power requirement which we need to propel the vessel. And when a ship is or when a vessel is approaching a shallow water, certain changes arises due to the hydrodynamic interaction between the bottom of the hull and the sea floor, like increase in the flow velocity between the bottom of the hull and the sea floor, and which in turn leads to increase in trim, increase in sink gauge and resistance. And we have analyzed using that model the resistance and power characteristics of the vessel under a set of speed ranging from 0 to 20 knots. These are the results we obtained using the software. Till the blue line border, it is the service speed which is 8 knot. The power and resistance characteristics are shown here. The first graph indicate the speed power curve, and the second one indicate the resistance speed curve. As you can see in the results, it is clear that up to the speed of 12 knot, the curve is going smooth, which means a proportional increase is indicated there. After that 12 knots, non-linearity appears there, suggesting that a significant rise in the power and the resistance for that particular vessel. And these are the outcome which we have reached after that analysis of the resistance part. I have discussed it with the previous slide. And this one, for the same model, we have generated the frictional resistance curve and the wave resistance curve. And it is, we obtained that in the first graph, you can see which is of that frictional resistance curve. It is in that as we go for low speed, the frictional resistance is becoming more predominant. And as we are increasing the speed, the wave making resistance is dominating there. And the results which we obtained is also satisfying with the theoretical expectations. These are some general points which we all know about the maneuverability in shallow water, so I am skipping this for the time being. These are the conclusions which we reached, that hydrodynamics in shallow water is differ from that compared to the open sea conditions, and the depth of the vessel and draft has a significant impact on the hydrodynamics of the vessel. And this study gives a literature review on the hydrodynamic forces and its interaction and different wave patterns. We analyzed the resistance. Maneuverability we haven't analyzed here, but we have given a literature review. Then we have conducted the analysis for the wave pattern, and we concluded that certain changes arises as the speed is changing from one regime to another, and the effects of variation of the parameters including the speed of the ship and the draft impact the vessel's hydrodynamic performance. So that was all about our presentation. Thank you all for hearing us, and we would like to do the computational analysis of that same particular vessel as a future work in term of the maneuverability and seakeeping part. Thank you.
Thank you. Right. So we have time, for a quick one or two questions.
Sir, I mentioned about Maxer software.
Maxsurf was used to model the hull form.
Yes, sir.
What about your resistance modeling?
Maxer modeler we use for the modeling the hull form, sir. And for the resistance part, we use Maxer resistance modeler.
Oh, Maxsurf resistance. Okay. Next question. Uh, did that give you a separate frictional resistance? What formula did you use? You haven't mentioned that. You have shown a frictional resistance curve. Yeah. How did you get that curve? The left side curve.
And the right side as well.
Right side also, yes.
in the Maxsurf resistance module,
No, what does the Maxsurf resistance module do? How does it calculate the frictional resistance?
we can input the method which we want to calculate the vessel.
What is the method?
We have used the Haltrop-Mannen method.
Haltrop-Mannen. Then you should be clear. When you present a paper, you must be clear about what you are using and what is the technique used to predict. For example, in the second curve, you see there is a drop there. What modeling is this?
No, sir. The result is that the service speed of that particular vessel is up to 8 knot.
No. Why is there a drop in the curve?
It will be humps.
About 18 knots, 17 knots.
Humps and hollows are there.
So if we are increasing that speed limit more than that, there will be variation in the graph, right? So that was the result over it. So the vessel cannot run more than that particular.
I think you require to do more than that. This doesn't show properly. Maybe you should do a better analysis than Maxsurf. And you should not extend the curve beyond a speed for which the vessel is meant to run. Non-linearity comes in and then you don't know how to control it. So you get some results. Some results which are not realistic. Because you are students, you are in third year, you should know these limitations of doing some work and presentation. When you present, you must exactly mention what is the method used, how it is used, and whether the data you are getting is reliable or not. Thank you. Good effort, but you require to improve yourselves.
Thank you, sir.
Thank you.
Right, thank you. The next talk is a study on the factors influencing hydrodynamic analysis on a shallow water region pipeline. This is a paper by a team from NIOT. You all are in NIOT, right? It's also a paper authored by three, all of whom are with NIOT. Paper will be presented by Anulekha Majumdar. She has been working as a scientist at the National Institute of Ocean Technology, specializing in ocean thermal energy conversion and wave energy technologies. She holds a gold medal in her MTech in ocean engineering from IIT Madras. At NIOT, she is involved in designing and developing mechanical components required to produce fresh water and electricity from the ocean. Design of cold water pipe responsible for carrying deep sea cold water to shore-based OTEC plant and wave energy to address India's growing energy needs sustainably. Anulekha. Yes. So this is a kind of continuation of the same pipeline project that was presented in our last session, right? Okay. So it's good to have a series of presentation on the same topic. So I look forward to hearing it.
Thank you for the introduction, sir. Good evening to all present. My name is Anulekha, and I'll be presenting on the topic a study on the factors influencing the hydrodynamic analysis of a shallow water region pipeline. So a brief about the kind of renewable energy technologies we do at NIOT. So as the name suggests, we work on ocean technologies, And from the ocean, we can get energy from waves, currents, or thermal gradients. So NIOT started its advent in the ocean energy technology from the wave energy plant, which was demonstrated in Vizhinjam in Kerala. It was a fixed oscillating water column based plant. Following the success of the wave energy plant, we dipped our feet in the ocean, and we tried to demonstrate a 1 megawatt OTEC plant. However, there were some issues with the connectivity of the pipe. And that project was not did not take off. So in place of that, we went for a 1 million liters per day low temperature thermal desalination based offshore barge mounted plant. And basically, low temperature thermal desalination is an offshoot of ocean thermal energy conversion. It works on the same principle, minus the turbine which generates the power, which I will show in the next slides. And after after the success of this LTTD plant, numerous LTTD plants were put up in the island of Lakshadweep. And currently, there are 7 LTTD plants supplying fresh water to the islanders. Other than that, we have also worked on floating wave energy converter devices such as backward bend ducted buoy and a navigational buoy which is functioning in the Ennore port, which provides navigational aid to the boats in the port. And other than that, we are also working on hydrokinetic turbine which generates electricity from the ocean currents. So basically, India is situated in the tropical area, and which has a very high surface seawater temperature of about 28 to 31 degrees Celsius. And to run an ocean thermal energy conversion plant, we need a temperature difference of about 20 degrees to get the output of the water as well as electricity. As you can see in the figure, India is lying somewhere around the dark orange zone. So it is a good site to get the energy from OTEC system. So basically, right now we are working on developing an OTEC power desalination plant, which will be coming up in Kavarati. So as I said, we already have put numerous LTTD plants in the island of Lakshadweep, but all the plants are getting the energy from diesel generators. And since we all know diesel is a fossil fuel, and it can have some negative impact on our ecosystem. So to make the system completely green and to have a self-sustained system, we are adding the feature of a turbine. Here, the circle one after the flash chamber. What happens in this is the warm water from the surface of the sea is taken and flash evaporated in the flash chamber. This is a low pressure chamber in which the warm water boils at room this temperature, very low temperature. So we don't need to reach 100 degrees Celsius for boiling the water. After boiling the water and making it into a vapor, we pass it through the turbine where it expands and produces electricity. And this expanded vapor then passes through a condenser where it is condensed using the deep sea cold water, which we draw from around 1000 meters of water depth. This water that is taken is around 8 degrees Celsius of water. And then this water condenses the water vapor. And the water which this condensed water which we get is the output. This is the fresh drinking water. So the main features of this plant is that it will give a continuous water. Only in the beginning we will draw power from the grid, but after the plant starts functioning, it will be completely self-sustained, because we are getting the power from the turbine. The turbine produces exactly the power which is needed for this system. So we are not right now producing any extra power. So as my colleague showed in the earlier session, that this is the this is the layout of the plant, and this is how the pipeline will look. So now coming to the topic, so basically we have a very long cold water pipe to transport the cold water to the shore, and which is made of high density polyethylene of diameter of 900 mm and the length of almost around 4000 meters. And we need a longer length because the water which we need, the cold water, as you can see in the picture on the left, that we need a water of about 8 degrees, which is available at 1000 meters of water depth. And from the bathymetry, we understood that this depth is available at around 3.5 to 4 kilometers of the from the mainland. And so for this pipe is having a very large aspect ratio. So for this, we need to carry out some analysis to understand how much of the weight is required to hold the pipe in position. And there should not be a huge lateral displacement of the pipe, and also the pipe should not be subjected to huge stresses and bending. So the simulations were carried out for two conditions: normal operating conditions having a significant wave height of around 0.8 meters and wave period of 6 seconds considering a John-Swab spectrum, and a current speed of about 0.5 meter per second. And a storm condition was considered with significant wave height of 6 meters and a wave period of 12 seconds, and current speed at the surface will be around 2 meter per second. So this is the outline of the pipe. Since this pipe, cold water pipe, is a naturally buoyant pipe, we need to place some weights on the pipe in between to keep it below the surface. Otherwise, it will have a tendency to float as it is naturally buoyant. So extensive analysis were carried out to determine how much weight is required. But other than that, we also need to find the top portion of the pipe is very critical for us because it will be susceptible to more forces. And so for that, we carried out analytical calculations using DNV code, and in-place analysis was carried out using OrcaFlex. So these are the forces that the shallow water region pipeline will be subjected to. Because of the wave and current, it will be subjected to drag, which is directly proportional to the velocity, square of the velocity. The lift, which will try to bring the pipe up, it will be in the vertical direction. Inertia, it's because of the acceleration of the water particle velocity. The friction will come into picture because of the soil resistance as it is laying on the bed, and the weight because of the self weight and the buoyancy. So the on-bottom stability of the pipe was estimated using DNV RPF 109, which is a standard given by DNV, and the water depths were assumed to be from -1 to -6 meters of with respect to the chart datum, and weights were estimated based on the breaker heights. So according to these calculations, the total weight estimated for this on 1 meter to 6 meter of water depth was around 63 metric tons. As per, since this analysis was done for a long duration of the pipe to check how the pipe is behaving when it is in place for a long time, we considered a marine growth thickness of around 38 mm and a drag coefficient of 2.5 and added mass coefficient of 4. For the pipe which is beyond the shallow water region, the added mass coefficient was considered around 0.6. As my colleague already explained, why we have taken HDPE as the material, and so I'll be skipping this slide. So basically, the bathymetry data was taken from the measured bathymetry, which we carried out using echo sounders. And the top end of the pipe was fixed, whereas the bottom end of the pipe was connected to a heavy clump weight. Two sets of chains were provided at 200 meters of the pipe length from the shore. This was provided to limit the lateral displacement. but they were kept as slack so that they don't take too much of the pipe weight in case of any failure. And to distribute the 63 metric tons which we received from the DNV